NASA's James Webb Space Telescope has recently provided astronomers with a cosmic revelation, offering a mesmerizing peek into the intricate world of exoplanets. The telescope's discovery of methane in the atmosphere of the distant exoplanet WASP-80b represents a significant stride towards comprehending the atmospheres of planets beyond our solar system. The groundbreaking research enriches our understanding of a remote celestial body and opens doors to a broader exploration of exoplanetary atmospheres. In this video, we'll delve into the significance and implications of this discovery for our understanding of exoplanet diversity and habitability. Join us as we explore Webb's first exoplanet discovery, understanding WASP-80b. The fascinating world of WASP-80b has intrigued both astronomers and space enthusiasts alike. Even though this planet's size and mass resemble Jupiter's in our solar system, it boasts a unique temperature profile, classifying it as a warm Jupiter. This distant planet is located in orbit around a red dwarf star in the Aquila constellation and is a staggering 163 light-years away from Earth. The challenges posed by its proximity to the star and its vast cosmic distance have prompted scientists to use innovative observational methods, particularly the transit and eclipse methods, to uncover the secrets hidden within WASP-80b. James Webb Space Telescope finds water and methane in the atmosphere of a warm Jupiter. The James Webb Space Telescope has achieved yet another milestone in exploring the vastness of space. Recently, it detected methane and water vapor in the atmosphere of a Jupiter-like world around 163 light-years away. This incredible feat was accomplished by observing the extrasolar planet WASP-80b pass by the face of its parent red dwarf star, which orbits roughly once every 3 Earth days. Astronomers have only discovered water vapor in the atmospheres of roughly a dozen planets thus far, and detecting methane using space-based spectroscopy has been even rarer. Thanks to the groundbreaking work of a team including Lewis Wellbanks and Michael Line of the School of Earth and Space Exploration at Arizona State University, along with researcher Taylor Bell from Bay Area Environmental Research Institute, the James Webb Space Telescope continues to push the boundaries of our knowledge of the universe. This was the first time we had seen such an obvious methane spectral feature with our eyes in a transiting exoplanet spectrum. Not too much unlike what could be seen in the spectra of the solar system giant planets a half a century ago, Wellbanks said. It's worth noting that the James Webb Space Telescope has previously detected atmospheric methane in other instances. One such example is the discovery of such molecules around the exoplanet K12-18b earlier this year. This suggests that the JWST is becoming increasingly adept at detecting the presence of methane in exoplanet atmospheres, which is a crucial step in the search for life beyond our solar system. A needle in a cosmic haystack, WASP-80b is categorized as a warm Jupiter due to its distance from its parent star. While not as close as hot Jupiters, it is still closer than the cold Jupiters in our solar system, such as the original Jupiter. However, its relative proximity to its red dwarf star poses a significant challenge for astronomers to study. Even with the capabilities of the $10 billion JWST, detecting the planet's spectral signal is equivalent to spotting a single human hair from a distance of 9 miles or 14.5 kilometers away. Nevertheless, astronomers have developed a way to tackle this challenge by waiting for WASP-80b to transit the face of the red dwarf it orbits and then observing the collective spectrum associated with the planet. This method has enabled astronomers to gain insight into the planet's atmospheric composition and temperature, and has contributed significantly to our understanding of exoplanets. Chemical elements and molecules have unique absorption spectra, meaning they absorb light at specific wavelengths. This characteristic makes identifying specific molecules in a planet's atmosphere possible by comparing the combined spectra to the star's solo-spectra and finding distinct fingerprints. To observe these spectra, scientists use the transit method. This method involves observing the system from our perspective as the planet moves in front of its star, causing the star's light to dim slightly. It's similar to when someone passes in front of a lamp and the light dims. By studying the light that passes through the planet's atmosphere during this transit, we can identify the specific molecules present and learn more about the planet's composition and atmosphere. As the planet rotates, the star illuminates a narrow ring of its atmosphere, located at the boundary between the planet's day and night. This atmospheric layer appears denser at specific wavelengths of light due to the absorption of light by the molecules present in the atmosphere. Consequently, it results in a more significant reduction in the amount of starlight that reaches us at these wavelengths, as compared to other transparent wavelengths. This technique has proved to be a valuable tool for scientists to analyze the composition of a planet's atmosphere by identifying the colors of light that are being blocked. Furthermore, the scientists needed to rely on more than one method to measure the atmosphere of WSP-ADB. They went above and beyond by utilizing an additional approach to gain a more comprehensive understanding of the planet's atmosphere. WSP-ADB has variation in its temperature, making it a unique exoplanet. All planets emit light through thermal radiation, which is also the case with WSP-ADB. This light's intensity and wavelength depend on the planet's temperature. Being very close to its star, WSP-ADB has a surface temperature of 551 degrees Celsius, which is significantly lower than the typical temperature of hot Jupiters at 1,177 degrees Celsius, but much higher than the extremely cold temperatures of our own Jupiter, which can fall as low as -148 degrees Celsius. Warm and hot Jupiters are giant gas planets that are tidally locked to their stars. This means that these planets have a permanent day side that always faces the star and is much hotter, and a permanent night side that always faces away from the star and is much cooler. Before WSP-ADB passes in front of its star, the planet's day side is directed towards Earth. This alignment allows astronomers to measure a dip in the light coming from the star during the eclipse, which reveals infrared light emitted by the planet due to its thermal emissions. This provides astronomers with eclipse spectra, showing light absorption patterns correlated to the molecules in the planet's atmosphere. These patterns appear as a reduction in the planet's emitted light at specific wavelengths, the best of both worlds. By combining the eclipse and transit data, the team determined the amount of light blocked and emitted by the atmosphere of WSP-ADB at different wavelengths. The researchers used two models to determine the levels of methane and water that could be found in the atmosphere of WSP-ADB. One model was strict and relied on existing physics and chemistry, while the other was more flexible and tried millions of different combinations of methane and water abundances and temperatures. The team compared transit and eclipse data to both models and concluded that they had detected methane in the planet's atmosphere. Exploring the chemical composition of WSP-ADB could provide scientists with valuable insights into the exoplanet's features, formation history, and evolution. By studying the methane and water abundances, researchers can infer the atmospheric carbon-to-oxygen ratio, which varies based on a planet's location around a star. This analysis could reveal whether WSP-ADB formed in its present location or was initially positioned further before migrating toward its star. These comprehensive studies would help us better understand the exoplanet and its origins. Not only is methane an essential gas in tracing atmospheric composition and chemistry in giant planets, but it is also hypothesized to be, in combination with oxygen, a possible signature of biology. Looking ahead to future discoveries with Webb, this exciting result indicates that we are standing on the threshold of even more thrilling findings. By conducting further observations of WSP-ADB with MRI and NIRCam, we can explore the atmosphere's properties at varying wavelengths of light. This discovery instills confidence that we can detect other carbon-rich molecules, including carbon monoxide and carbon dioxide, allowing us to create a more complete picture of the atmospheric conditions on this planet. As we discover methane and other gases in exoplanets, we can expand our knowledge of how chemistry and physics work under conditions different from those found on Earth, and soon on other planets that resemble our home planet. One thing is clear: the James Webb Space Telescope's discovery journey is packed with potential surprises. We hope you enjoyed this video. As always, please be sure to share your thoughts down below on this intriguing new discovery, and don't forget to subscribe to our channel for more thrilling space updates. Thanks again for watching, and see you next time.